Hello, welcome back students. In the last session we studied the difference between a junction field effect transistor and the MOSFET. In that we studied how the depletion MOSFET and enhancement MOSFET works. What do you mean by transfer and output characteristics, and what are the applications of the MOSFET? What is the difference between junction field effect transistor and MOSFET? All these things we studied in our last class. In this session today, so we are going to study introduction to operational amplifier. Now the question comes, what is an operational amplifier? A operational amplifier is a versatile component, and the name operational amplifier because it can be used in many functions or many applications such as integrator, differentiator, adding, summing, subtraction, and filter, signal condition. All those application operational amplifier can be used. That's why the name operational amplifier came into the picture. In the diagram, my dear students, you can see in the diagram, this is the symbol for the operational amplifier. This is the symbol for the operational amplifier, where this is called as inverting input and this is called as non-inverting input, and this is our output. Other than that, we are giving bias by using plus VCC and minus VEE. So now this is the circuit diagram for the practical operational amplifier. In the practical operational amplifier, the circuit diagram you can see, the operational amplifier will amplify the different signal. Here you can see voltage at the inverting terminal. Here you can see voltage at the non-inverting terminal. So our operational amplifier will amplify the different signal. That's why it is called as VD. And this is the gain block. This is the input impedance between the two terminals, and this is the output impedance of our operational amplifier. So now the electrical equivalent model for ideal operational amplifier. So in the ideal operational amplifier, there is no connection between the two terminal. That means input impedance is very high. That means input impedance is very high or infinite, and you can see here output is shorted. That means output impedance is 0. So that is the difference between practical and ideal operational amplifier. My dear students, now I'll take you to our notes, class notes. So first we will see generalized voltage amplifier model for generalized voltage amplifier model for model, or it is also called as Thevenin's equivalent model. Thevenin's equivalent model consists of normally voltage source and resistance. So here you can see this is the amplifier section. This is the our amplifier section. This is our amplifier section, and this is the input source what we are going to connect, and this is the input impedance, source impedance. This is the input voltage, and this is the output load we are going to connect, and it is output voltage. So AV high, where A indicates open loop gain. Open loop means when you are not connecting anything from output to the input, it is called as open loop. And VI is the input voltage. So output voltage is the multiplied by A into VI. This is called as Thevenin's equivalent model. Thevenin's equivalent model for a generalized amplifier, and it is called as generalized voltage amplifier because if the input is voltage and output it will amplify the voltage only. That's why it is called as generalized voltage amplifier model. Now my dear students, we will move to the difference between ideal and practical operational amplifier. So you can see the various parameters we are using to compare the difference are: first one is something called as bandwidth, second one is slew rate, third one is open loop gain, fourth one is common mode rejection ratio, Fifth one is power supply rejection ratio, input impedance, output impedance, and offset. You are going to study all these parameters, but when you compare ideal operational amplifier and a practical operational amplifier, we are using these parameters to compare. Bandwidth is, in the case of ideal operational amplifier, is infinite, means infinite bandwidth is available, but practically the operational amplifier, here we are taking 741, it works for only 1 megahertz bandwidth. Sleeve rate is infinite, practically it is 0.5 volt per microsecond. Open loop gain is infinite, but practically this one is a common mode rejection ratio, power supply rejection ratio. Input impedance, I said input impedance for ideal operational amplifier is infinite, but practically it is 2 mega ohm. Output impedance, we show output is shorted in the this one ideal operational amplifier, but it is 0. Output impedance is 0 in that case, but practically it is 75. Like this, these are the difference between various parameters with respect to ideal operational amplifier and practical operational amplifier. So this is the IC, my dear students. We are using operational amplifier 741, op-amp 741. You can see it is 8-pin IC. So here you can see this is the inverting terminal, and this is the inverting terminal. This is a non-inverting terminal. This is the output terminal, VCC. All those things you can see. Now we are going to study the various parameters of operational amplifier. These are the various parameters. And if you study all these parameters, then it will be very useful. So from the exam point of view, they may ask to write the different operational amplifier parameters, or they may ask you to explain the different operational amplifier parameters, or they may specifically ask 3 to 4 parameters. It depends on the marks allotted to the particular question. So we have to study all those things. We will see that in the next session. Thank you. Hello friends, welcome back. Now in this session you will see the parameters of or performance parameter of our operational amplifier. As I said in the previous class, there are several parameters: bandwidth, sleeve rate, open loop gain, common mode rejection ratio, power supply rejection ratio, input impedance, output impedance, and input impedance, output impedance, and offset and drift. So now we'll see one by one bandwidth. First one is one by one. Now first one is the bandwidth. So in this example, we will take the operational amplifier 741 for our explanation purpose. So now what is the bandwidth? Bandwidth is nothing but a range of frequency over which my amplifier works. I repeat, bandwidth is nothing but a range of frequency over which my amplifier works. If you take any amplifier, can it work on over any frequency? The answer is no. If you take any amplifier, it will work on particular frequency range, that is called as a bandwidth. Now this frequency range is related to the gain. So here I will try to draw x-axis, nothing but frequency, and y-axis is nothing but gain. Y-axis is nothing but gain. Gain is nothing but AD. Y-axis is nothing but gain. 1 minute. I will try to draw y-axis is nothing but gain, and x-axis is nothing but frequency. That is, x-axis is nothing but frequency. Y-axis is nothing but our y-axis is nothing but AD. That is called as gain. Normally, AD gain is expressed in terms of dB. Gain is expressed in terms of dB. So now what is dB? dB means 20 log AD, 20 log bracket AD, 20 log bracket AD. This is the gain. So now at frequency 0 or at initial frequency, we will take this is the gain. This is our gain at initial frequency. But now the question comes, if I use infinite bandwidth, that means infinite bandwidth means the frequency is infinite, then is this gain remains constant? No. After frequency of minus 3 dB, after frequency of minus 3 dB, or after certain frequency, the gain actually decrease by 3 dB. Gain actually decrease by 3 dB. So we will call this is 3 dB decrease, 3 dB, and then it will continuously reduce. And at particular point, the gain reaches to 1. So AD is at particular point, AD is equal to 1. That means 20 log AD, 20 log 1 base 10 is equal to 0. That means when the gain is 0 dB, this curve will cross this curve or intersect this curve at particular point, and that particular point is called as unity gain bandwidth, or bandwidth and gain combination, unity gain bandwidth, that is called as unity gain UGB, unity gain bandwidth. So normally the bandwidths are expressed in two ways. The first way is sometimes they will express by UGB, unity gain bandwidth. So bandwidth represents the frequency range over which the amplifier works. This is the first one. Now move on to the next parameter. Next parameter is called as slew rate. Slew rate is the parameter describes how quick the output changes to a particular value within a particular time period. For example, if the output of the operational amplifier changes to 4 volt within a microsecond or within second, then slew rate is we call 4 by 1 microsecond. If output reaches to 6 volt, then it is called 6 by 1 microsecond. That is called as a slew rate. So in the other way of explanation of slew rate is something like this. So this is the time, and this is our input Vi. So initially we think our input is 0. I make our input to 1, logical 1, or I will make our input, I will make my input to logical 1. This is logical 1, input to the logical 1. Now I will call this as a logical 1. But what about the output? As soon as I make my input logical 1, whether the output changes in that same speed? No. Answer is no, because it takes some processing or time or delay due to the other gates and processing delay. So my output is slowly rises and it overshoots. It will come down again and it will overshoot again and come down again, and finally it will settle. This is called as this settle. So now slew rate will measure by using this slope. The slope of this slew rate, the slope of this curve. For example, here this is the change in the output voltage for this amount change in the time. So slew rate is normally expressed something like this: change in the output voltage divided by particular time. We will call it is in a micro or microsecond. We will call this is in a microsecond. So if you take one more waveform, something like this, the slew rate of this one is slower compared to slew rate of this one. So this is called as a slew rate. The third parameter is settling time. As I said, my output will raise, it will overshoot, and it will come down, and it will overshoot, it will come down. So it will take and finally it will settle, but it will take infinite amount of time. It may take infinite amount of time to settle. So we cannot wait till then. So we will consider a particular range of tolerance band, and when the output reaches within that band, then we will say the operational amplifier is settled. So here I can say the operational amplifier output is in this range, so it is settled. And this T2, this is T2, and this is our T1. So this is the settling time of the operational amplifier. Our operational amplifier. So this is the third parameter, settling time of our operational amplifier. So we have already studied now what is slew rate, And we know what is open loop gain. Open loop gain is nothing but it is nothing but AD, and AD it is nothing but output voltage V0 with the input. Input is nothing but VD. What is VD? VD is nothing but difference in the input voltage between inverting and non-inverting terminal. This is called as open loop gain. Otherwise, open loop gain is the gain when we don't connect anything from the output to the input as a feedback. That is called as a open loop gain. So input impedance. So we have already know ideal operational amplifier. Input impedance is the input resistance between two terminal. For ideal operational amplifier, it is infinite. For practical operational amplifier, some input impedance is there. So in the same way, output impedance for ideal operational amplifier, the output impedance is 0, but practical operational amplifier, the output impedance is in some ohm. So we have seen the settling time, as I said previously. See, this is called as a tolerance band for the settling time. So we have studied settling time and slew rate also. So with this friend, we will see the rest of the parameters in the next session. Thank you. Hello students. In the last session, we saw some of the properties of operational amplifier or op-amp. So the properties are nothing but bandwidth, slew rate, settling time, then output impedance, input impedance. Now in this class, you will see the other properties such as common mode rejection ratio, such as other properties such as common mode, we call it as common mode rejection ratio, and second one is power supply rejection ratio, third one is offset and drifts. These are the three properties we are going to see in this class. Before that, let me explain bandwidth. In the last class, I told you bandwidth. Bandwidth is nothing but in the last class I told you bandwidth. Bandwidth is nothing but a range of frequencies over which my operational amplifier works. So if I take here if I take x-axis as frequency or time and y-axis as gain, normally gain is expressed, as I said in the previous class, over decibel, and we know what is decibel. Decibel is nothing but 20 log. It is nothing but 20 log AD. This is decibel. So at zero frequency or at lower frequency, normally if you take this is our gain, after certain frequency our gain will reduce at 3 dB and it will reduce further if you increase the frequency. And this reduction is something 20 dB. This is 20 dB for decade. This is called as 20 dB for decade, or minus 6 dB for octave. These are the two parameters we use, minus 6 dB for octave. 20 dB decade means we plot this frequency over decade scale. If you start, this is 1, this is 1, this is 10, this is 100, this is 1000, this is 10,000, so on. So the gain decreases 20 dB per decade. For example, if F1 is my frequency, at F1 the gain is 100 dB. Now at 10 F1, now my gain is 80 dB. It is decreased by 20 dB per decade. If you take the other parameter is used to express when my frequency double, that is, initially my frequency is F1, after that my frequency double means 2F1, after that my frequency double means 4F1. This is, in order to express this one, we are using dB, octave scale. So, at F1 it is 100, then at 2F1 it is 94 dB, at 4F1 it is 88 dB per octave. So this is the scale we use, this is the parameter we use to express the gain. So with this, friends, we will now proceed to the other one, that is called as CMRR. What is CMRR? Common mode rejection ratio. We know the gain AD. We know the gain AD is nothing but V0 by Vd. What is V0? V0 is the output voltage. What is Vd? Vd is the difference voltage between the input. This is called as output gain or differential gain. So we have one more thing that is called as common mode gain, AC. AC is nothing but VO by VC. Now what is this VC? VC is nothing but the average of two voltage at inverting terminal and non-inverting terminal, or average of common mode voltage. Normally the common mode or operational amplifier should amplify difference voltage. It should not amplify common mode voltage. That means VC should be zero. AC should be 0. That means common mode rejection ratio is nothing but the ratio of AD by AC. That is how operational amplifier reject common mode signal. That is an indication of common mode rejection ratio. Theoretically, AC should be 0. When AC should be 0, for ideal operational amplifier it tends to infinity, but practically it is not infinity. This is called as common mode rejection ratio. One more parameter is PSSR. That is nothing else, power supply rejection ratio. What is power supply rejection ratio? Normally, when there is a change in the power supply signal, that is power supply voltage, that is VDD or VCC, etc., output should not change, but practically output changes. Suppose this is delta V is the change in the power supply. Delta V is the change in the power supply, and V0 is the output. Then power supply rejection ratio for positive changes, positive power supply variation. We are using two power supplies for operational amplifier. This is called as power supply rejection ratio. Similarly, power supply rejection ratio for negative variation in the power supply. Negative power supply variation is nothing but variation in the power supply, negative power supply, and output. So this is one more parameter, and the last parameter we are using is called as drift and offset. What do you mean by offset and drift? Now let us take operational amplifier. So this is our operational amplifier. We will take this as, this is inverting terminal and this is a non-inverting terminal. So this is inverting terminal and this is non-inverting terminal. This is the output. Here we are giving Vi inverting, and here we are giving Vni, that is non-inverting. And this is nothing but our difference voltage Vd. This is nothing but our difference voltage Vd. And we are getting the output based on the open loop gain AD and Vd. That is our output. That is nothing but our output V0. Now what will happen if I short this and this input terminals, if I short these input terminals, whether my output V0 is 0? No. No, the answer is no. If I short this input terminal, output is not 0. There is a small voltage at the output. So in order to correct that voltage, what I will do, I will add a correction voltage source at the input. I will add a correction voltage source at the input. I will add a correction voltage at the input. This is non-inverting and this is inverting. I will add correction voltage, whether it is a plus or minus depending on it. And when I vary this voltage source, this I will call as a IOS, voltage source, VIOS, voltage source. When I vary this one, I will vary this one to make the output is equal to 0, and normally this voltage is called as a drift or offset. So these are the important parameters of our operational amplifier.